Hello. Today we're going to talk about the very basics of organic chemistry for an undergrad kind of level, and some of it will even be a refresher. So we're going to talk about molecular orbitals, bonding, and hybridization. Now, of course, because in organic chemistry most things are primarily about carbon, that's where we will start. So just a reminder. Our carbon has 4 electrons, and as you know, the outer shell of most compounds can only fit 8 electrons in total, so that leaves 4 spaces for bonding. In carbon, you have 1 electron that is in an S subshell, and 3, which are just the others, are in a P subshell. Now, just to remind you, S subshells can have a maximum of 2 electrons, and P subshells can have a maximum of 6, and D subshells, which are not relevant in carbon but it's still useful to know, can have a maximum of 10 electrons when bonding. So let's have a look at what these kinds of subshells look like. So in an S subshell, the electron density is pretty much just a sphere. So this is what that would look like. And a P subshell, it has 2 distinct lobes, which are probably much more symmetrical than mine, but there we go. And a D subshell has 4 distinct lobes of electron density, but again, that's not relevant in carbon. So if we think about carbon again, so we can go back up, and we look at how many P subshells there are and how many S subshells there are, we know we have an electron filling 1 of the S subshells and 3 filling the P subshells, and 1 space in the S for bonding and 3 spaces for bonding in the P subshells. So because we've only got 1 S subshell filled with electron density, let's have a think about how the P subshells will look in carbon. So there are 3 axes that we can think about when thinking about carbon. So we have an x-axis, a y-axis as a useful, and a z-axis. So that creates a 3-dimensional space. And you will have a P subshell along the x-axis, so that's px, a P subshell along the y-axis, which will be py, and a P subshell along the z-axis, which will be pz. I mean, that's now an awful picture, but I think it gives you the idea. So now you can see that you would need 3 of the P subshell orbitals to fulfill the maximum of 6 that we talked about earlier. So let's talk about what actually happens when carbon makes bonds. So we now know that carbon has 1 S subshell and 3, sorry, that's really awful, let's try that again, and 3 P subshells. So when carbon bonds, obviously if they're all different shapes, there's going to be an increased electron repulsion, which obviously we don't want. So what happens is these orbitals, they hybridize so that they're all the same shape if there are only sigma bonds formed. So they hybridize to a shape that looks something like this. So we have 1 large lobe and 1 small lobe, and there are 4 of these, and that is called sp3 hybridization. and it happens to decrease electron repulsion. So the electron density is in the large lobe, and that's the bit that does the bonding. So this type of hybridization only happens when there are only sigma bonds, so when there are only single bonds. For instance, in ethane, so there's one single bond there, and 3 on either side. So all of these bonds would be sp3 hybridized. But something different happens when there are double bonds involved, when there are pi bonds involved. And let's have a look what happens using ethene as an example. So let's just draw our normal sigma bonds with our hybridized orbitals. So those are the large lobes on the hybridized orbitals, and here's where your hydrogens will be bonded to your carbons. So those are all hybridized orbitals, and that is called sp2 hybridization, because the last p orbital doesn't actually become hybridized because it needs to be able to form the double bond. So that would form a pi bond. Look something like that. That's obviously a terrible picture, but it does look something like that. So that is sp2 hybridization, and that happens because one p orbital is left to form the pi bond. So that would no longer have a tetrahedral shape, whereas this one would have bond angles of 109 degrees. But this one would then become planar because of the pi bond that needs to be formed. And obviously, if there is another double bond formed, so if it's an alkyne, such as ethine, then you would have sp hybridization, which is pretty much the same, apart from 2 of your p orbitals aren't hybridized, and just the p and just one s are hybridized to form one bond for each hydrogen. So that is basically everything. So if we scroll up and kind of recap what we've learnt, so we remember that carbon can form 4 bonds, because it has 4 spaces for electrons, and one of these orbitals are for it is an S-shaped subshell, and 3 of them are P-shaped subshells. So the S can only have 2, and the P can have 6. S is spherically shaped, and P subshells have 2 lobes with a node just in the middle there. And then they hybridize to form this shape here with one large lobe and one little lobe. So there's no longer these defined different shapes. It's sp3 hybridization to form a tetrahedral 109 degree shape, except in the situations where there is a pi bond formed to create a double bond, such as in ethene or ethine. And that is everything.